So, welcome everyone to this doctoral defense. My name is André Teixeira. I'm an associate professor here at the Department of Information Technology, and I will be sharing today's session. So, let me start by introducing to you those that will be involved in this defense. We start, of course, with Wenqing, the doctoral candidate who will be defending her doctoral thesis. And Wenqing has been supervised by Professor Christian Honor from Uppsala University, Professor Timo Voigt, also from Uppsala University, and Ambush Varshney, now at National University of Singapore. The supervisors and myself don't have an active role in the defense. That's all for the other people that I'll be introducing. So after Wenqing, we have the opponent, Associate Professor Aysan Al-Asania from EPFL in Switzerland. Then we have the examining committee. We start with Nikki Trigoni from the University of Oxford in the United Kingdom, Professor Danny Hugs from KU Leuven in Belgium, and Professor Mikkel Sternat from Uppsala University, the Department of Electrical Engineering. So we also need to thank Docent Torben Vigran for accepting to be a reserve, but fortunately your duties are not required at this moment. So having introduced everyone, I'll now give a brief overview of the proceedings. So we will start with a brief overview of the research area by the opponent. Following that, we'll pass over the token to Wenqing for her to give a presentation of the main contributions of the thesis. At this point, we'll have a short break, 5 minutes, to rearrange the room a bit. And there will be then the second phase of the defense, which is discussion between the opponent, the examining committee, and the PhD candidate. So first, there will be a discussion led by the opponent and the doctoral candidate. At that point, once the discussion is done, then we'll go to the examining committee, where we'll take a round robin of questions around the topics of the thesis. Once that is done, then there will be room for the audience to ask questions as well. Then we close the session. The examining committee meets in a private meeting to have the final deliberations. And in parallel, the candidate and the audience, you're most welcome to go to the 6th floor for some refreshments while you wait for the decision. Yeah. With that, and before I hand over the token to the opponent, I would like to ask Wenqing, do you have anything to add to the printed thesis? Thank you. Then I'd like to give the floor to the opponent for the brief overview of the research area.
Hello, thank you all for being here for Wenqing's defense. So Wenqing's kind of a topic centers on IoT, and there is a lot of interest in IoT because all of the potential applications in industry, manufacturing, health, kind of agriculture. And two kind of the big challenges in IoT, which Wenqing tries to address in her kind of thesis, are kind of power, right? The lower the power of an IoT node, the more practical it is to deploy, the more scalable they are. And kind of security. Security for IoT is always kind of one of the big problems, just because if you want to employ kind of cryptographic methods, they tend to consume so much power that makes them impractical to deploy in IoT nodes. And so Wenqing's kind of topic on IoT focuses on backscatter or battery-free IoT. So these are kind of IoT nodes that don't have a battery. They rely on an external power source, like an RF power source. If you've heard of RFIDs, the RFID tags you see on clothes, this is kind of what backscatter. They don't have any power source. They just use RF signals to power up. And the problem with these is that they're great because they don't have a battery. You don't have to worry about replacing a battery. They can last for years. And kind of they're very cheap. But the problem is that they don't have a good range. You cannot kind of get to communicate with them at distance. So if you think of like farms, you would need a kilometer range if you were going to deploy sensors in a farm. So there's been recently a lot of research on extending the range of these kind of battery-free backscatter nodes. And some of this work either uses ambient signals like TV signals, or tries to use Wi-Fi kind of signals from your Wi-Fi to power up the tag and kind of relay information over that signal, or kind of a power source. And people have shown kind of that you can get almost a kilometer range if you kind of design these tags in certain ways. But to be honest, I've read most of these papers. And if you read most of these papers, you kind of get to the end and you realize that while they are able to achieve a kilometer range, so the receiver is a kilometer, let's say, away, the tag needs an emitter or some power source that is at least 1 meter away from it. And so it's always kind of disheartening to read those papers, because it starts with a great vision and you're very excited. And then they kind of hide this in the implementation section where say, well, we need kind of a transmitter that emits a sine wave to power up the tag, and that's 1 meter away. And so I've always felt that, okay, this is kind of not going to make it to practice. If you're going to have an emitter that's 1 meter away, it might as well that transmitter sends the data. Why do you need the tag? And this is kind of where the first part of Wenqing's thesis comes in, to say, well, no, we can design these tags that the emitter can be almost 100 meters away. And so making these things much, much more practical. And so in the first part of her thesis, she focuses on basically that aspect, making them low power and making them able to power up using an emitter that's 100 meters away. And so she does that using kind of a novel architecture using tunnel diodes, which she'll speak about. And in that part as well, she tackles another problem, which is with something called Li-Fi. So if you don't know what Li-Fi is, it's something when I was kind of a grad student, there was a lot of hype about it. It's basically using light, your lamps, to send data, right? But kind of for a while, it's been having a hard time taking off. And when you talk about people who work in this topic, they tell you that it's just very hard to change the infrastructure. It's very hard to it's IoT nodes with RF are much more common commodity hardware. And Wenqing kind of also tries to tackle that problem in the sense that, can we use the RF at least on the receiver side? Can we use kind of the IoT nodes that kind of have RF as is, don't change anything about them, add something that bridges kind of light to RF. And so that's the kind of second subpart of the first part of the thesis, focused on low power kind of communication. So the second half of this thesis focuses on security. And as I said, kind of one way to do security is to use encryption or authentication or cryptographic methods, but typically these consume a lot of power. And in fact, you see that whenever they're being used on low power devices, they're being hacked. There's a conference called DEF CON where every year they hack RFIDs, and they hack just because you cannot put like very power hungry, kind of very efficient cryptographic methods on these. And so Wenqing's approach is to focus on something called fingerprinting. And the idea is that every radio, every kind of hardware, the manufacturing process is not ideal. They don't end up exactly the same. There's some imperfections in the manufacturing process that creates like unique fingerprints in the hardware. And again, this is a topic there's been so much work on it. And I myself tend to be skeptical because how robust these techniques are. And this is exactly what Wenqing tries to address, is how can we make them robust? How can we make them work efficiently and reliably in kind of real settings? And she tackles it also for backscatter, and she tackles it on how to build an end-to-end system, which is like kind of the last paper in her thesis, on base that makes this entire thing efficient and doesn't consume a lot of power. So overall, kind of the thesis, as I said, tackles two topics. And what I really like about this thesis is that kind of it took stuff that I personally have been skeptical about, to say like, are we really going to use backscatter and get the 1 kilometer? Because all of these previous work kind of hid the fact that you need to be 1 meter away. All of the previous work on fingerprinting is not very robust. And this is exactly what Wenqing tries to do, is kind of tries to make these things more practical. And another aspect of this thesis that is kind of very important is that she doesn't only kind of propose techniques, she actually builds the hardware and builds the protocol and builds the system and demonstrates end-to-end, right, communication. So this is tends to be very difficult. This takes way more time than just doing simulations, than just even just building the hardware. You need to know everything from RF circuits all the way to networking protocols to communication systems. And so that requires a very wide of knowledge. And that's what's exciting about reading her thesis, because it gives you this in simple terms, this overview and all this background to be able to understand the innovations that she does. So with this, I'm gonna stop and let Wenqing present her thesis, and then I'll ask her questions afterwards. Okay, go ahead.
So first, I want to thanks everyone being here, especially thanks my opponent and all the grading committee members fly a very far distance and to come to my defense. And in this presentation, I will introduce the research work I conducted with my colleagues in the past 5 years of my PhD journey. And let's begin. So my thesis title is Design and Identification of Wireless Transmitters for Low Power and Secure Internet of Things. So the philosophy of Internet of Things, I feel it's like forming an information network, and the building blocks is embedded devices. So there is a really remarkable revolution ongoing for embedded devices. But these devices is different from general purpose computers. It's normally coupled with specific requirements on its form factor, cost, or longevities. And that constrains them to have limited resources. So here I give a quick glance about the embedded devices revolution over the years. And we can see, and find my pointer. Yeah, we can see this is a telespeed devices 20 years ago. It's at the size of your hand and powered by 258 batteries. And now we see what we have today for embedded devices. So the embedded devices can be battery-free and light like a dandelion, which is dispersible by the wind, or wireless microsensors sensing your biometric data and can be implanted in human bodies. Or even it can involve actuators to be micro robots at the size of 1 penny. So many innovations pushes the revolution of embedded devices to become smaller, low cost, and most importantly, with very long longevity. So running on either small batteries or energy harvested from the environment, which poses the low power as one fundamental design criteria. So now let's look at the power consumption of existing wireless embedded devices. So in one such devices commonly consists of a sensor, which sensing the surrounding environment and converts the sensing matrix to signals, and the signal then be processed by microprocessors and then transmitted out to other devices. And in the scope of my thesis, this transmission mainly handled by the radio frequency transceivers. And wireless communication, of course, is a cornerstone to network different devices together. Now let's look at the power draw to conduct these 3 functionalities. We notice they are not at the same level, and then the communication, wireless communication dominates, which consume several times more than other tasks. So there is a pressing need to reduce the power consumption of wireless communication, and in this thesis, we mainly focus on the transmission part. So backscatter offers a promising approach to significantly reduce the power consumption of communication from milliwatts to microwatts level. But backscatter have a primary concern, which also mentioned by Hai-sung, is a limited communication range. So especially in combination with active radio, this really bothers the real deployments. And the first part of my thesis is propose a novel low-power transmitter architecture to elevate this challenge. And we keep the power consumption also under milliwatts at the microwatts level, but offers a better communication range. Now we move on to the second part of my thesis. So let's zoom out a little bit and think about devices connected together. The increasing connectivity enable many diverse applications. And the embedded devices handle more and more sensitive data, like your biometric data, your heartbeat, or your glucose level. Such information is really sensitive and want to be protected. So the importance to secure these devices is steadily growing. And one fundamental question is device identification and authentication. So conventional approach commonly use digital ID, which is information stored in the memory. And it's involving resources intensive operations like encryption, decryption, and for keys, we also need key exchange, distribution management. And normally, higher security level means more resources need to be occupied. But IDs does not need to be bit level informations. And especially when we consider the occupied resources, the devices we talked about is with very limited resources. So we don't want to put extra load on such kind of device. And in my thesis, we focus on a passive identification method, which utilizes the transmitter radiometric fingerprint. So the receiver identifies the transmitter, use unique characteristics embedded during the signal generation. And this method is passive towards the transmitter, so it does not put extra demands on them. They just communicate and transmit the data they want and move the major overload to the receiver side. So this is really fit well with devices we talk about with limited resources, like and also consume low power. And in addition, this fingerprint is embedded in the transmitter hardware, so it's more difficult than bit level information to change easily. So although radiometric fingerprint has been proven effective, but is not ready to be utilized in practical deployments. Ideally, when a receiver received a frame, he needs to identify the transmitters with its fingerprint reliably in a robust manner. But the propagation of wireless signals from the transmitter to the receiver is influenced by multiple factors like the distance and the surrounding environment. So when the surrounding environment becomes complex, the fingerprinting accuracy is really hard to maintain. And my work focuses on enhancing the robustness of the fingerprinting system under the diverse wireless conditions. And now let's move on to the receiver side. Although fingerprinting method puts a major load on the receiver, but current setup use really bulky and expensive equipment, at least use USRP for signal acquisitions, and also computers to conduct this fingerprint. But it's not practical to think about the real deployment scenarios. So my work make contribution to bring the fingerprinting system to the low power and low cost embedded devices. And in addition, new radio communication technology like backscatters also bring new opportunities because it has a fundamental different composition of electronic components. And we conducted case studies to explore these new chances. In general, this part of work follows the direction to move the fingerprint more practical in the real deployment. Now we move on to the details of my thesis. So it includes 6 papers, and in collaboration with my supervisors and also my colleagues. And there's 2 short papers published on the peer review workshop and 2 long papers published on ACM SIGSAC and SIGMOBile flagship conference. And there is also the last two papers is under review. And the first one, we just got the revision reviews from the transaction of mobile computing. And this is a thesis overview. As listed in the title, the thesis mainly focus on the wireless transmitter. And the first topic center around low power. So covering two papers, and we make contributions on low power transmitter architecture design. And the second topic reserved around the keyword secure, and we use the fingerprint in the signal to identify the transmitters. So the major part is about radiometric fingerprint and also channel robust fingerprinting system. And we also have a small piece of work is touch a little bit channel fingerprint only. And in this presentation, I will cover both of this topic and 4 major papers. So let's start the first part. The first part is about low power wireless transmitter. And let's first look at a conventional wireless transmitter. So the data is formatted and modulated on a low frequency signal by altering its frequency, phase, or amplitude. Then commonly this part is handling digital signal. So we convert it to the analog signal and pass it to the RF stage. And the RF stage, firstly, it mixed with a high frequency signal and converted to the design RF frequency band. And then this high frequency signal passed through amplifier, filter, and finally convert it to electromagnetic waveform by the antenna. Nowadays, the transmitter, like I said, they involve digital components, but also need analog components. And with the processing speed and energy efficiency of digital component increasing dramatically, nowadays, most of the baseband and even intermediate frequency band operations is handled by digital components. However, the RF stage, which mainly handles high frequency operations, remain using mainly the analog components, and especially including the analog mixture, oscillator, amplifier, and filter. So, but analog components does not scale like digital components. At the end, the steps in the RF stage dominate the power of the entire wireless transmitter. And backscatter provides a solution to reduce the power consumption. The idea is it decomposes the steps in the RF stage and deploy them on 2 devices. So the emitters specifically handle the power-hungry operations of high-frequency carrier generation, and the passive tag, which serve as a data source and performs a low power modulation by reflecting the external signal. And it conducts this reflecting operations using RF switch. So therefore, by doing such kind of low power modulations, the power consumption of the tag can be significantly reduced to tens of microwatts. But in ideal backscatter scenario or backscatter deployment scenario, the emitter should be shared by multiple tags, and these tags can be designed in a simple and low power manner. But consider the practical deployments, the tag also has the flexibility to locate it in a reasonable range around the emitter. But backscatter in practice, to achieve a communication range of tens of hundreds meters, it needs the tag to locate it close to the emitter, which is a few meters away, and also this emitter need to be strong. So it's this phenomenon become more obvious when it requires a slightly higher data rate, which is tens to hundreds kilobits per second. And a too small distance, as Haisam mentioned, is impractical in real-world deployments because it failed to highlight the advantages of backscatter over the conventional active radio. And the reason behind this is due to the fundamental backscatter reflection-based mechanism. We can use a phrase equation to elaborate this reason. So the backscatter tag reflects the external signal which already propagates over distance d1 and experience a path loss. And the tag, during the reflection operations, it could not 100% reflect all the energy, so it commonly has 3 to 5 dB more return loss, which we show it as the delta. And after the information is modulated on the signals, the modulated signal carries information and go through the communication range D2 and finally reach the receiver. So there is two types of the loss. The first, we have a term named dual pass loss. So it first goes through the signal goes through the D1, which doesn't carry the tag information, and then goes through the communication range D2. And the second, beyond that, during the reflection, it also have a extra loss. So consequently, to compensate this loss, if you want to achieve a relative high communication range, you need the emitter device to radiate a strong signal and to locate it really close to the tag. So in our work, we rethink these backscatter mechanisms and propose a new idea. We use tunnel diode self-oscillating mixture. If you are confused about this, don't worry, it will become clear in a second. And different from backscatter, this kind of reflection-based mechanisms which use RF switch, we use a new philosophy which integrate the power-consuming steps in the RF stage and in a power-efficient manner, so it can achieve a similar power consumptions as a backscatter, but it will have less dependency on the emitter device. Next, I will introduce this design in 3 steps. First, the tag locally generate an RF carrier signal. With the design, we use a typical component, which is tunnel diode. So tunnel diodes are negative resistance device. It means in their IV curve, there is a regions when the voltage increases, the current decreases. So this kind of performance can provide gain in the circuit. And when we coupled with a LC tag circuit, it can be used to design an oscillator, and more importantly, this oscillator resonant at RF frequency. And another really important property about tunnel diode is this regions happens in an area which has low voltage and low current, which brings its low power performance. So the tunnel diode oscillator can generate an RF carrier signal, but this signal is weak. At most is minus 17 dBm. And another more significant challenge is its instability. So the carrier signal easily drift due to the ambient environment changes, such as temperature, humidity, and of course time, and the nearby motions. And it's very designable to have a transmitter with a noisy oscillator. So we sidestep its stability via injection locking. Injection locking is a phenomenon when there is an external single tone signal at close range, frequency range, as a tunnel diode resonant frequency, incidents the circuit. So the tunnel diode will synchronize with this external signal, and also its stability got improved. And one important feature for tunnel diode is it only needs a very weak signal, which is as low as minus 70 dBm, to achieve injection locking, get improved stability. And the last step of this design is we leverage the non-linearities of tunnel diode, which enables it to have the mixture behavior and turn it to be a self-oscillating mixtures. We call it SOM. So it has by default a significant advantages over backscatter. The reason is backscatter using R switch, which controlled by a digital signal to achieve mixing. But digital signal by default has a really poor spectrum efficiency, and it will leak to the adjacent channels, causing interference and prevent the coexisting with other devices. But in our designs, we enable the mixing with analog signals. So it will prevent the generation of unwanted harmonics and also get a better spectrum efficiency. At the end, this is a judo communication system. It has a really similar system setup as backscatter, but emitter plays a really different role. And judo transmitter is different from backscatter in a way that it conducts local oscillator functionality and also mixing with a baseband signal, especially analog baseband signal, on board together and in a power efficient manners under 100 microwatts. And the emitter device play a really different role. It's utilized to stabilize the noisy judo transmitter. And because the judo transmitter only need a weak signal to achieve the injection locking, so the dependence between the emitter and the transmitter is significantly weaker than backscatter. And another property of judo transmitter is a weak transmitter, but when working at sub-gigahertz frequency band and also coupled with a high sensitive receivers, it can reach a really good communication range. So at the end, we achieve the communication range more than 100 meters, especially when the emitter is located far away from the transmitter, which is more than 150 meters. And the good things is we achieve this performance at the data rate, which is 100 kbps. Now we move on to the second part of my thesis, which is about fingerprint. So first, let's talk about where does this fingerprint come from. Due to the manufacturing variance, the electronic components has imperfections, so they exhibit inconsistent performance. And during the signal generation, the components will leave unique characteristics in the transmitted signal, which can be used to identify different transmitter. And in our work, we mainly focus on two types of imperfection. The first is in the frequency domain. So the generated signal frequency is deviate from the intended one, which mainly a result of oscillator imperfections. Second, during the modulation process, like here I give example about OQPSK from 15.4. And the generated symbol characteristics deviate from the ideal one, which show in the blue dot. So this is mainly due to a lot of different imperfections. For example, IQ in quarter-to transmitters, the IQ branches imbalance, and the imperfection coming from the components like DAC, amplifier, and filter. So to capture these fingerprints at the receiver, we embed the feature extraction in a coherent receiver processing chain. And different stages be utilized to extract different features from the side information during the demodulation processing. So synchronization stage is mainly used for frequency domain features extractions. And after that, we got synchronized the signals, and the symbols in the constellation can be used to extract the modulation domain features. And all the work I will present is based on the AO2 15.4 protocol. So here is an overview of a fingerprint system. The receiver uses the signal processing mechanisms to extract the fingerprint features. Then the fingerprint profile is be passed to the pattern matching modules. And in our cases, we use a data-driven classifier to judge its identity. And there are two stages during the system operations. In the enrollment, it's when the device is first joined the network. So the receiver collects its fingerprint, which is mainly used to train the classifier. And second stage is identification, is when the system needs identification or authentication service. It calls the fingerprint system and asks them to judge the identity based on the incoming signal fingerprint. And to help you understand the results I will mention in this presentation, I simply introduce the majority evaluation matrix it will show. It is a true exception ratios. We name it in the context of identification, or you can understand authentication system. It represents the capability of the system correctly identify a device. And for one specific device, it's the number of samples which the identifiable label is equal to the actual label divided by the total of samples with the actual label I, which is a sum of the row marked in green. And in the result I mentioned next, it will be an average value among all tested devices. So as I mentioned at the beginning, in this thesis, we focus on 3 research questions around this topic. The first one is wireless channel disturbance. So the challenge here is the transmitted signal is not directly observable by the receiver. And instead, the receiver will got a compound of both the transmitted signal, which carries imperfection, and also the transit impact from the channel. So when the channel impact dominates, the fingerprint system face challenge to identify the device accurately. And we did experiment with 40 different sensing boards. In clean environment, it's really easy to maintain a good identification performance, and especially over multiple measurements. But if we move to the practical environment, it's really hard to maintain as good performance in the wireless, in the practical wireless environment. But when we think about our daily environment, it of course involve bunch of the complex wireless phenomena like refraction, reflection, scattering, and particularly it's also time varying. So it's posed a challenge to fingerprinting system. How could we enhance the robustness of fingerprinting systems in different scenarios? Let's first look at the reason why it will ruin the accuracy. We use a feature space illustration to explain this. Here you can think S1 and S2 is 2 fingerprint profile from 2 devices you collected in the enrollment process on the specific wireless channel condition. And you use this to train the classifier, so you got a decision boundary. We simply just draw a line in between. But during the identification stage, highly likely the channel condition is different. And for challenging wireless channels, the magnitude of the deviation risk to go across the decision boundary, which ruins the classification accuracy. In our work, we go one step further to look into details about how wireless channel distort the fingerprint. We specify our scope for 15.4 at 2.4 gigahertz and indoor scenario, and we recognize 3 major impact factor, which is multipass, Doppler, and noise. So we use the fingerprint samples collected in the clean environment, which is in the anechoic chamber as input, and use statistic wireless channel models to simulate different channel impact factors. And we found each of them impact the fingerprint in a really different manner. So the simulated multipass samples forms a similar trajectory for different devices, which we can see from here. And the Doppler only show obvious impact when the speed is very high, about above like 10 meters per second. But in the daily scenario, we consider the impact with low speed movement is negligible. And the noise deviate particular features and also result in high random noise left in the synchronized constellation forms a cloud here, and then which increasing the variance across the fingerprint samples. So we deploy 2 strategies to deal with major impact, which identify as multipass and Doppler, multipass and noise separately. So the first strategy use prior training, which deployed in the enrollment stage to handle the multipass impact. So the idea is data augmentation, but with the support of wireless channel knowledge. So our system generates a hybrid profile for each devices, and it's including the enrolled device's fingerprint and also simulated version under different multipass channels. So by doing this, we can optimize the decision zone to guide the classifier better fit the practical multipass channel, which we'll show in the identification stage. And for noise, we deploy a sliding window to reduce the variance. And for feature which susceptible to the noise, we use the signal-to-noise ratio as an indicator to compensate them. And in the evaluation, we use 40 devices from 4 different kinds, 4 different types of the boards, and the sample collected in clean environment as the enrollment profiles. Then we test the proposed system performance in 3 different indoor environments with 13 setup. It covers different distance, line of sight and non-line of sight setup, and also moving object with human movement speed. And here we can see the system we proposed achieve a consistent good performance with average true accepting ratio consistently good for all tested devices. And now we move on to the second part, which is backscatter fingerprint. So radiometric fingerprint, as I introduced, is a passive identification method. So it fits really well with the low power, low complexity philosophy of backscatter transmitter. And backscatter transmitter has a different composition of electronic components in a way which it delegate part of the components to another devices, which is emitter. This separation among the emitter and tag enables the possibility to identify both of them. So we conducted a case study about this, and most existing and all existing backscatter fingerprinting work mainly focus on RFID, which in the scenario with a single emitter, and in this work we emphasize the identification of multiple emitters. To give an impression of the relation between emitter and tag fingerprint, let's first look at the feature space. For visualization, I transform the high-dimensional feature space using linear PCA to the 3D. And for tags sharing the same emitters, there is a distinct cluster between different tags, which can indicate the potential to identify the tags. But when there is a multiple emitters and different tag may be powered or reflecting the signal from different emitters, we can see each emitter forms a cloud. And in each cloud, it has similar behavior like shown in the previous figure, which indicates the possibility to identify the emitter. Then we design the system with a purpose to identify them separately. So we train to classify with different targets. And we tested with 6 emitters and 10 different backscatter tags. And we can see emitters classifier and tag classifications can both achieve a good performance. And in tag classification, we tested 2 scenarios. The first one is it's powered by it's backscatter the same emitters, and second is like we don't know which emitter it's powered. It's backscattering, and we just blindly identify the tags. Now we move on to the last piece of work. Although fingerprinting is a passive towards the transmitter, but consider practical deployments. You also need to consider the receiver side, and it's important to make the system applicable towards the real low cost, low power embedded devices. But existing work, including the previous 2 I just presented, is all using the phone setup, which rely on high speed, high cost signal acquisition equipment, like oscilloscope, spectrum analyzer, and at least software defined radio, and also need dedicated memory and computational resources, normally handled by the computers. So this setup is too heavy and expensive for the real deployment. And there is several reasons behind. For signal acquisition part, the fingerprint feature, because it needs to detail analyze about raw signals, which requiring a high resolution sampling rate. And the raw signal data for commodity receiver is commonly not available. And it's only give you some statistic metrics like RSSI, LQI, such kind of things. And second, most systems put high memory requirements to store the signal samples, which at a high sampling rate, so the data size is relatively high, and also need to store the intermediate values during the feature extractions. And also, some fingerprint profile is actually quite large. They are depending on the row signals, row IQ data. And finally, the feature extraction and classification require dedicated signal processing capability. And in this work, we investigate the feasibility to implement a complete radiometric fingerprinting system on a low cost and low power commodity off the shelf SoC. And we choose the NRF55 series. It cost only €6 each. And recent year, there is a rising support for BLE directional finding functionality, which becomes a chance to tackle the first challenge about high resolution signal acquisition. So in the direction of finding, it needs detailed analysis because you need a phase to determine the relatively directional relation between the transmitter and receiver. But this function is designed specifically for the directional finding, so it has multiple constraints. And in this work, we hack the stacks and find out a proper setup to repurpose these modules as a continuous signal acquisition modules. And finally, we can achieve up to 8 megasamples per second sampling rate, and we can continue sampling one frame up to 500 microseconds. And for the feature extraction part, it's basically the same as the work I proposed at the beginning, but we implement in C and do a bunch of the several steps of optimization to make it efficient and can be handled by these smart chips. And for the classify part, we trained a random forest classifier offboard using our computer in Python, and then we converted to C and achieve the onboard inference. This is a final performance of our system. In the evaluation, we tested 32 devices from 4 different types, 8 of each type, and it achieved on average 92% accuracy. And for the resources footprint, it occupied half of the ROM and a little bit more than half of the RAM and a little bit more than half of the ROM. So one thing I want to mention here is the classification part. We didn't do any optimization, so it's just a converter to C. There is no compression happening and no quantization, which for neural network. So there is much of space can be improved from this part. And the energy consumption is slightly higher than 12 millijoule. And as a reference, the same chips, when the receiver listens the channels, it consumes around 20 millijoule 1 second. And it took 1.2 seconds to fingerprint 1 frame. So up to now, I already covered all the details about my work I want to introduce. And here I want to summarize a little bit the contributions. So the thesis focus on the wireless transmitter. And the first part, we introduce a new idea, a new architectures, which use internal diode. It's different from backscatter, and it tackles the challenge of backscatter communication. And in the second part, we focus on identify the transmitter using radiometric fingerprint, but most of my work is the goal is aligned with the direction which enable the vision to of wide spreading fingerprint system in practical scenarios. And at the last, I list few future work directions I feel very interesting. The first one is standalone tunnel diode self-oscillating mixture transmitter. So in our designs, we use injection locking, which requires external emitters to achieve a stable transmission. But this is not the only way. There could be several different ways, alternatives to solve the instabilities. For example, we can achieve injection locking through another channels, which is not as same as the one we do through the air. that will also make the systems simpler. Or we need innovation in the circuit, because we found out the instability is mainly from other devices on the board. So there is other ways if we can compensate this drift, so it also can make it stable. And the second direction is because tunnel diode oscillator has instability, so we can utilize it. It can be utilized to do sensing. We conducted the hand gesture sensing, and also it can be used to material sensing and other sensing tasks. And from the fingerprint side, its fingerprint not only can be used for security reasons, it also can be used to improve the communication qualities, because different transmitters, they have their different fingerprint, which make their communication quality not as good. The things is coming from the hardware, but at the receiver, you can from the software to fine tune your parameters specifically for specific transmitter to improve the communication quality. And the last direction is, of course, extension of the onboard fingerprinting. The onboard fingerprinting is a short paper, and we didn't do. There is a bunch of the places we can do optimization. For example, the classification, classifier deployments. We can deploy more lightweight classifier, and also the classifier can be improved in terms of it can handle more critical problems, like the one I mentioned here is about unknown devices. This is also needs the innovation from the classifier point of view to handle it. So up to now, this is all my presentation, and thank you for listening. And also I want to thank again all my collaborators for all my papers. Yeah, thank you.
Thank you, Wenqing. So this concludes the first part of the defense. Now we'll have a break, so I propose that we come back for the batch to make it easier to see. And we will have the rest of the defense here on this area. So when you come back, if you want to move to the side of the room, that would be. Thank you. Hey, welcome everyone to the second part of this defense. So we now have the discussion between the opponent and the doctoral candidate. And once we're done, then we'll move over to the exam committee. So, virtual discussion.
Yeah.
Okay, shall we start? So we'll start with the kind of first part of the thesis, and then we'll move. And one thing maybe I want you to explain is the emitter that you use for injection locking.
Mm-hmm.
Is it also being used to power up the judo tag, or is so you use like some energy harvesting or battery to power it?
So unfortunately, this part in this works, particularly we didn't involve the energy harvesting modules. It's still powered by batteries.
Okay.
So, but we coupled this part of design in our follow-up work.
Mm.
So that actually a better way to demonstrate the capabilities. We get quite exciting results from that, coupled with different energy harvesting resources. Like for this work, is only focused on communication.
For this paper.
Yes.
Great. So that leads me to my next question.
Mm.
When it comes to kind of backscatter,
Mm-hmm.
there is two kind of things that limit the range.
Mm-hmm.
One thing is what you talk about in your thesis, which is the fact that you need two-way communication, that the signal has to go to the tag, reflect, and rather than having 1 over the distance squared, the signal decays with 1 over the distance, the first distance times the second distance squared. So, but another thing is the powering up, right? It's being able to harvest enough energy to power up. And I'm wondering, in your experience, which which is affects the range more? The ability that kind of to power it up to be close enough to the transmitter, or the actual two-way range? So because sometimes, so let me ask it differently. Sometimes if you put the stack close enough to the transmitter, they kind of, it still doesn't matter because the receiver is so far, and the two-way distance, like the two-way reflection, kind of affects it much more. But sometimes, like, it's more, if you put it a bit farther, like in the middle, right, you would assume that maybe that kind of is a bit better, but then it doesn't power up. Like, do you have a sense of which affects the range more? Is the ability to power it up, or the kind of path loss for communication?
Let me see. So I think if you cannot power it up, which means you basically cannot conduct the communications. So, but that extent is like, I feel like it's the same class. It's different questions in my opinion, because the way to, you see, like, it's too far away from the source, so you cannot power it up. That is about, especially I think you mentioned is like RF harvesting, this kind of method, so they can, it's distance it far. That is matters like if it can work, it's if it still it can work. It's a kind of impact can work or not. If it cannot power, it cannot work either. So it cannot have communicate anything. But the problem we tackled is communication range, which is it's a kind of like it's already be powered up.
So do you think you envision that it will kind of be powered up like using another method like solar or some?
Yeah.
Okay.
I think we didn't constrain it to be RFID cases. So to say we in our other work we cover other different type of the energy harvesting technology, including vibration and solar panel, and also RF is one part. So I feel like RFID is really typical scenarios, which is of course it's been widely deployed, and that means it's really useful. But it's to enable backscatter to have more diverse applications. Of course, you cannot constrain harvesting not to a specific one.
Okay. So my next question is, let's say the emitter is very far away at 100 meters, right? And I'm wondering, by the time it reaches the tag, the signal is kind of very, very low power. So I don't know what the numbers you get, say minus 80 dBm or something in that range, just above the noise floor, good enough to kind of do the injection locking. But then if I were to kind of generate that signal at very low power, wouldn't I be able to put it on the tag itself? Like, I don't know RF circuits, so I'm not, but basically understand that oscillators consume a lot of power, and if you want kind of a stable oscillator that generates a stable signal at a reasonable power before you amplify it, then it's gonna be kind of very power consuming for that. But is it possible to kind of generate it at very low, very, very low power and then use it, have it be stable? Or is it that you could argue that, okay, this is exactly what I did. I tried to generate it at low power, but it turned out it's not.
So the things like I read some related work, more electronic engineering part about RF circuit design. And they actually, there is a way to do injection locking. Normal way to do injection locking is put it on the same circuit. So they use a high stable local oscillator and to injection locking a low stability oscillator. This is normal way to do that. So think about like if we implant similar idea to our circuits, like you said, we have a weak oscillator at RF. I would say that's actually would be a direction to explore. But the problem is like if you put external oscillators, the power consumption of course will increase. So if that still have enough benefit in terms of like low power, that's a question we need a lot of RF engineering to try, test, and explore that. By default, RF oscillator is really power consuming. So I think that's needs to do real test to see if there is possible to have weak and low power RF oscillator can be put on the same circuit and how much benefit still can get. That needs to be investigated.
The next question is, can you explain a bit your choice to abandon backscatter, so not kind of use backscatter? Like, would you think that kind of why not have it tunnel diode with backscatter, or kind of is it the decoupling to the radiated power from the node from the emitter kind of really has kind of this big benefit to be able to increase the range?
So I think I have two parts in your questions. The first part you ask about I think you ask about the backscatter point scenario, and if you have tunnel diodes, this type of transmitter, what new possibility can be expanded. So for backscatter, I don't think backscatter is not a bad technology at all. It's really great. But they have specific deployment scenarios, I think. For example, if you think about a smart home scenario, you have, for example, just a few meters or like tens meters. This kind of a small range, backscatter will be really good options because if you put it 2 meters away from the emitters, and then the tag can be better free and like a sticker form factor. That's really good fit for backscatter. But if you think about a little bit longer communication range, for example, in industrial factories or farm, like you mentioned, agricultures, that needs certain more like communication range. But that will put backscatter in it's not really fit.
So you think the only way to improve the range is to kind of not use backscatter because the fact that the signal has to endure 2 path loss?
I think for the longer communication range, it constrained. It's not really a excellent choice for backscatter, especially you consider flexibility of deployment. And for judo is actually also not perfect. We have trade-off made in the systems, but judo actually work perfectly together with backscatter. The reason, maybe I can use like the slides. This is also shown in our papers. It's about when we increasing the emitter device strings, the backscatter mixed signal strings vs judo mixed signal strings. We found there is 2 regions. When the emitter device signal is weak, we have a really good benefit and good gain. That is a pain point of backscatter, is when the emitter signal is weak. So you barely can really backscatter a strong signal. But judo can do that. But in another way, if you think about really strong emitters, judo doesn't win too much. So that means actually a good combination of judo and backscatter will provide a more comprehensive solution in terms of when your emitter device is varying from large range, either weak.
Like, can you detect if it's high power and then decide to use?
I think you can have a bunch of ways to detect it. We didn't deploy these things. We haven't deployed that things. That is just, we analyze, we think that will be like, we have energy detector control there. This is not deployed.
Okay.
But that will be architectures have probably more like scenarios.
So you talk about kind of trading stability for low power, right? And the fact that the tunnel diode is not stable, it drifts, right, over time, and then that's why you need the emitter. And I'm wondering, maybe you can explain a bit more why kind of stability is so bad. Like, why can't I just correct for it at the receiver? Because if the receiver doesn't need to be high power, maybe it can have a bit larger bandwidth, and the fact that it drifts, yeah, the kind of the center frequency drifts a bit, big deal, right?
First, I want to admit that is one solution to these problems. And we did also experiment in our papers. We don't use any external meters. If the surrounding environment is quite stable, and it's actually, of course, can communicate. It's not that it's barely can communicate. It's not that bad. It can communicate and even communicate over floors. But when we think about more practical scenarios, of course, you have this kind of disturbance coming from the surrounding environment. And when it's more ideal, you have a stable transmitter. But the things you ask, why it's so bad? So why it's so bad? It's actually, we analyzed the circuit. We found actually there is two reasons. The reason causing like temperature, humidity, or even time, the reason causing that may be different from the reason causing the motions. Because in general, tunnel diode by default is a really stable component in terms of temperature changes. But the circuit generates the oscillations is really susceptible to the temperature. The reason is not the tunnel diode's components, it's other components in the elastic circuits. Their capacitor, inductors, changes based on temperature that leads to the drift in the frequency. That can have several ways to do that. For example, what a lot of oscillators doing, they use compensation mechanisms. They use another components which have inverse changing trend than the components to compensate that. Or they deployed more stable capacitor or inductors. That's also another way. But when you talk about motions, we find out motions is because we didn't have really good isolation about two directional signals. So the signal is flowing out and also flowing in. And because backscatter, because tunnel diode, these components is really sensitive to really weak signals. So a little bit signal flowing in already enough to change the resonance frequency. But if you want to solve these problems, you need a good isolators design at the antenna part to make them not only flow one directions and not flowing back. So
I guess also the fact that it's narrow bandwidth, you cannot correct. It's harder to correct for the motion. Because I assume that somehow you can model all of these things and plug them into the channel. That's kind of like you have the wireless channel, and then you have some channel on the hardware that's being affected by kind of the motion from outside, right? Typically, motion creates Doppler, right? But kind of somehow you're saying it's kind of leaking back in and affecting the oscillator. And maybe that's hard to model, or even if you can model it because you're narrow band, it's hard to correct the case. Like, is it that it's just hard to model what's happening and compare? Because what I'm thinking is, and I mean, there's an argument against that as well. Well, my receiver can be high power, and I'm just gonna oversample the signal and kind of correct for all these distortions later on. And kind of, is that kind of, you know? So I understand there are other ways to mitigate this on the transmitter side.
This part I totally agree.
Yeah.
I think the receiver, because what we say, the drift is tons of kilohertz. It's not that really wide to cross megahertz. So there is possibilities if you can from the receiver to compensate it and to that's of course a way. But another things I want to mention also is not only frequency is drifting,
Right.
there is also phase noise. So we
Mm.
see from the, maybe I don't have, but from spectrum, if you after injection locking, the peak is much narrower.
I see. The phase noise.
Yes, that's also play a role.
Okay.
So that is two aspects. So that aspect, I think, of course, you can have really
Yeah, that's
good
harder to
receiver
approach.
to compensate the phase also. So in general, I don't think the idea you propose is a bad way.
Mhm.
I just elaborate from the transmitter side, and also I think the receiver side is a way.
So, I have a question. I don't know. You have figure 4.1 where you compare all these different kind of
4.1, okay. Yeah.
techniques in
I
terms
think
of,
I have even this one.
yes.
Mhm.
And one thing that surprised me is that even when you increase the data rate in judo from 100 kilobits per second to 10 megabits per second, you don't see kind of a huge increase in power consumption.
Yes.
I'm wondering why.
So first I need to explain the way we measure the power, or the way we indicate power consumption here. So we only measure the front end power consumption.
I see.
It's not including the baseband. Of course, if you
So
have
that
a,
will go into the
yes,
I see.
so the baseband, if you increasing, of course, the baseband power consumption will increase, but this one is only the front end. So the reason we didn't reach that is because you see here in the backscatter power consumption, it's actually the data they proposed is getting from different way. So some is from the real hardware measurement, some is from IC simulations, and for IC simulation, of course, that can reach really excellent data, excellent numbers here. But for us, we didn't do the IC simulations, so we choose to only use our equipment to measure the front end. Of course, if you comparison with a measurement with the same circuit and the measurements doing in the IC simulation, even without baseband, the IC simulations, of course, will give you a lower one. So that is what, in my opinion, the judo we measured is relatively high. If there is a way we can implement it in IC,
Yeah.
that will be even lower. That is the question you ask about why is that.
Yeah, okay, so that makes it clear. This is the front end.
Yeah.
Just before I forget, so you don't use a PA, right? And so
Yeah.
I know, what is the emitted power?
Yeah, we mentioned in the presentation. So the highest emitted power of the oscillator, what we measured is minus 17 dBm, and on average is minus 19 dBm. So when you talk about mixed signal, the mixed signal at the highest, it can reach almost the same strong as the oscillator, the carrier frequency of the carrier signal. But for if you have different baseband, like let's say if a different emitter strengths, the mixed signal also will vary. So that's yeah.
So let's describe. So since we're on the slide, so in this graph, it's kind of quite impressive. The kind of lower the only kind of thing that's yeah, you. And I'm wondering, kind of, how do you think kind of judo can further beat LoRa? Is it kind of if you use CSSS, or is it kind of reducing the data rate because kind of the LoRa backscatter has very low kind of data rate, or increasing the transmit power because this is mainly distance. I don't know the emitter power in judo and LoRa backscatter are the same, or
Almost the same.
oh, okay.
Yes, yeah, there are the boundary which the FCC regulation.
Okay. So what do you think is kind of limiting?
I think you touched two major points already. So the first is CSS. The chirp modulations give you 20 dB more, on average 20 dB more gains. So that can further reach the doodle. I think we'll be actually using to cross the LoRa. And the second is, of course, data rate. Data rate matters many things. For example, the receiver sensitivities. And that can give you another extra boost to the communication range. So I think you already say the answers, which I want.
So did you try to reduce the data rate?
In our experiment, we didn't do 3 kbps for the outdoor experiment. The reason is actually we did here, and the 100 kbps already reached the end of this.
Okay.
So we didn't try to do further. And but I believe it will give you a higher communication range for sure. Yeah.
So future kind of question. So what is kind of what would it take to make this Judo more kind of deployable? Like what is left? Like is it that if someone builds it into an IC chip and it's even going to be much more lower power, it's going to work great, there's kind of nothing left to do, or is it that there's still kind of a lot to do before it can be deployed?
I think for Judo, in my opinion, there's still a lot to be done. The ideally, when we write this paper, we send to the conference. The most reviews we got is like the reviews just got so excited about this, like free run mode. So it's no injection, nothing happens. Why it's good? Because it's basically a single transmitter. You don't need this complexity about emitters and such extent and blah blah things. That will be a game changing. But in order to do that, there is a bunch of the more work need to be. It happens, and beyond that, if we really reach that point, of course, making IC is one must go step. And one challenge for backscatter for fraternal diode is, of course, it's actually really popular in last century, but now it's not too many manufacturers is building, is produce it. So how to make it in IC is also a really significant challenge.
So people have not built it into ICs, they just build it as components.
Yes, because it's actually last century components we are using. So it's a really old components. But turned out this good performance in terms of like this low power, and also it's pretty good in the radio frequency band. These two properties actually have bunch of the opportunities in this century. So there is a lot of other work also focused on the diode.
Sorry, I didn't follow what you just said, because so why is it a forgotten technology? Like why is it that now is kind of the application or the right application for it, and that's why now we can use it? Or like is there like why didn't people use tunnel diodes before to kind of use the self-oscillating sort of, right? Or so is it that now the right technology has come, or the right kind of application has come for it, or is it there's something else that people did not use it?
So tunnel diode, I think mainly is probably about its manufacturing process and also the cost of this component. That is why it's been replaced by much cheaper components for its functionalities. But it doesn't have this kind of specific phenomenon. They didn't have put extra requirements on its power consumption. It's here that much. So that is why it's replaced by other semiconductor components, and it's fade away a kind of in centuries. And for us, we are the first one to using tunnel to design this. Or we find the phenomenon of self-oscillating mixtures. So it's not listed in the history to say, okay, that is mainly the way to using it and such kind of things. And
what was it mainly used for?
It's mainly used to
Just the divider?
Yes, just use a diode and only use for expensive equipment like oscilloscope. Yes.
So you do kind of mention this in your presentation. I had this question, so I want to ask you what kind of other novel kind of uses of tunnel diodes there could be, and you mentioned something towards sensing, and I'm wondering like why you did hint a bit into this now, but like what while I was listening, I was like, this is a device that is kind of sitting in the circuit. Why would it be with gestures or
It's not about this component. It's more about this tunnel diode oscillator designs we have. We found we'll think about it's if it's unstable, if it's not to be used, we're brainstorming if not be used for the transmissions, could we use for other purpose? And the good thing about this tunnel diode oscillator is really sensitive. Like in terms of like, if you have a really small motions nearby, you can see a few kilohertz like shifting during the frequency. So this sensitivity maybe can enable some fine gesture, this kind of detections. And because of it's also low power, so it could be have really nice application scenario like you have a really small tag and you'd be able to detect the motion around, or even deploy it in, for example, in industrial factories, detect the vibration of machines if it's working normal or abnormal, because it can be so low power and designed in a really simple way. So that is why I go to that direction. Yeah, that is the reason initial motivation why I go to that direction.
yeah, the last question on this part. So in your thesis, you mentioned something about reflection amplifier and modulated noise communication. Maybe you can tell everyone what these are. But my question is, like, do you envision that there can be better techniques than using kind of a tunnel diode, or is it kind of complementary? Or maybe for people who haven't tried the thesis, you can tell us just what are these.
I think tunnel diode definitely have like reflection amplifier is really like backscatter mechanisms. So they also design tunnel diode oscillators, but the way is they are changing the bias voltage to the on and off, and this changing happens in digital. So it's like backscatter to on and off and reflecting the external signal. So it's have a really actually much more spectrum efficiency because this tunnel diode has a gain and it will amplify the carriers. It also will amplify the harmonics. So it has a much worse spectrum efficiency. And for the noise modulations, that is a new come out research. And the people think about if the carrier is so power consuming, you don't need to put it to the radio frequency. Why not just modulate some signal already existing in a circuit like noise? Noise.
How is this different from the ambient backscatter where
you don't need any external signal?
So it's from signals on the circuit itself?
Yes, it's from noise from the circuit. Okay. So you don't need power. You need energy to make it to be modulated, but really low because you don't need this extra emitters.
So the point of having the extra emitter is that they are above the noise floor, right?
Yeah.
So how is it that if you're taking something at the noise floor, you're able to?
So first of all,
I know this is not your.
Yeah, I'm not the expert about that, but as far as what I read is like they are using they like backscatter, so they are changing the impedance, but they are not impedance. They are changing the resistance of two terminals, and the different resistance have different what they call noise temperature. So in the noise floor, you can see it's of course as a noise floor.
So it changes the noise floor.
It doesn't change the noise floor. You can see this footprint in the spectrum, like in the frequency domain. You can see this footprint about different noise temperature. the noise floor in different spectrum is different. So that's the way they are doing the noise modulation. But of course, you can see this. There is a really significant trade-off. At least now, noise modulation is really slow in terms of like the data rate is only can be BPS, so a few BPS. So yeah, this research has come up like the past 1 or 2 years. Yeah.
Okay, so I'll now switch to the second part, which is the fingerprinting. And one kind of question I always had about using radio fingerprinting for kind of authentication is I've always kind of imagined that you need maybe at some it's going to be the initialization is very expensive, which means like at some kind of when you kind of fabricated manufacturer, you need to do these tests to extract these feature and kind of uniquely identify them and then kind of use them. But what you said is that, well, no, that's not how we do it. When a node joins kind of the network, we extract these features and we map them to its ID, and that's how kind of we do it. And one thing that kind of confuses me about kind of this approach, apart from the fact that now anyone can come and say like I am node, right? So I can be an unauthenticated node that come and say, well, I am Wenqing, right? And there's no way to kind of verify. And then now the attacker is the one who's kind of, if it joins the network first before kind of other nodes, then it can steal their ID. But even if we assume that no such thing happens, that we only kind of try to detect people who are spoofing later on.
After this
yeah. So I'm still kind of confused about the enormous process, especially when you use kind of machine learning, because you have to do the training at some point, and training, requires a lot of data. And how do you do it if a node just joined the network and you don't have enough training data? And
you mean this question is focused on a new devices join the network?
Yeah.
How they train them?
Yes, because if the assumption is that at kind of in the factory I need to run all these tests and kind of do the training a priori, it seems like very complex from a manufacturer perspective to come and say, well, all these kind of RF radios that I produce, I now have to kind of manually test them one by one, fingerprint them, and then send them before they send them out. I mean, they don't do that today. They don't put them in anechoic chambers and they just manufacture, right? But at some point, the training needs to happen, and the training requires the data. And if you take your approach, which is more practical, which is when the node joins, we extract these features and now we map them to that node. But then if your kind of classification is using machine learning, not something like simple like shortest distance or kind of some simple approach, now you need training. So that's something I'm confused. How would you make this practical if kind of?
I think the question you ask touched different aspects. I will start with if you need a lot of data to do the training of this question. So the approach we tested, the answer is not that many data. The reason we tested with it's not like if you train a models, you need like thousands of these samples. In our testing, we did push it to 20 and even 5. So 5 samples you collected.
I would have assumed if you wanted to be robust to the environment, right? Because that's what you're trying to do, is to say, kind of, I'm gonna do this augmentation using the channel and kind of make it more robust. Yeah, if you want to make it more robust, don't you have to collect it in under different channels and kind of collect more data?
So
I understand with what you did so far, maybe low data wasn't
Yeah.
right.
So the way we did is if you say, in order to tolerate different wireless channel, do I need to collect the data under different wireless channel conditions? That of course really time consuming.
Yeah.
And this piece of work doesn't take that approach. We use the support from simulations to do that. Of course, it will put extra computational resources in to generate these simulations, simulated profile, fingerprint profiles. But in comparison with you conducting new experiments to cover different wireless channel, that's already cheap. And I think this is a way to empower the kind of to utilize.
So what you're saying, when let's say a node joins the network, I take its signal, and then I extract I take it, and then I kind of pass it through different in simulations, add more multipath, pass it through additional multipath channels, which are very different, and that creates a large data set that. But then you need to do the retraining, right? For your kind of whether SVM or random forest or all these techniques, you have to do it, right?
Yes.
Okay.
This part we didn't tackle in our research about if new devices join, how could you make your retraining lower cost to be more efficient? This part we didn't touch. But I think like methods like transfer learning, which you already have a model contains certain amount of information, and when you want to add more into that, so you can maybe what I talked about, maybe not for SVM, but more neural network, maybe you train some layers in that is enough to convince more information from the new devices. But that means that is the work need to put on the classifier part. So yeah, that's another directions of the work different from what we did here. Yeah.
So you mentioned kind of in your talk that kind of these radiometric fingerprints, these hardware, they're very susceptible to kind of heat, humidity, aging. Like over time, they change. And I'm wondering, like, how do you address this? Like, is it that you redo the training at some point? Like you say, okay, I trust now all the nodes, let me re-extract all the features, or kind of do you kind of cool to kind of say, well, if the temperature increased, then the oscillators are by this much. Like, how would you kind of tackle this issue that because that kind of to improve the robustness, that's right, essentially.
I think the work we conducted is focused on the wireless channel part. It's not say we cover everything. That's first piece. And in our experiment, we kind of conducted the experiment in different time, and it's course more than 8 months time.
Okay.
And in slightly different temperature, which is have above like 5-degree difference. And we mainly put the scope into like indoor scenarios. Under that conditions, the fingerprint we work on have enough robustness in terms of time. If you say, if that will change for longer time, we don't have the data to support that assumption. But aging is a really important problem for components. So it's, of course, we are aging to some extent. Maybe it would deviate to that point, which is make the classifier bad again. And this will means it needs retraining. Like you said, it of course needs recalibrate and need retraining. But in our test, we say it's already 8 months, so the training will be not like several days you need to retrain again, several days you need to retrain again when we talk about aging issues. So it's, of course, you can do more to compensate that. But this is what we say it's already can enable some applications in the daily scenarios. And for temperature, Actually, we conducted experiment in really cold weather in Sweden outside. We see the fingerprint changes. And
Especially at this temperature.
especially in temperature, it's cross 30 degrees. So we tested at indoors is 24 around, and we tested outdoor, which is -10. So it's really challenging for electronic components to maintain a stable stable performance under such big temperature variance. So the fingerprint indeed changes. And the way we observe is like they have certain patterns. For a certain temperature, certain fingerprints will have. That means it indicates there's a possibility you can compensate them or you can model them. But
Yeah.
Yeah.
Well, I guess if it's kind of the temperature in the environment, then maybe you can incorporate that as input to your classifier, and that can make it more robust. But sometimes it's also the hardware itself, right? It heats up because of all the components.
for that part, I don't think that for a normal board, of course, if you think about if it's really conduct a really intensive operation and make it heat up really a lot, if that will matters, I think will. But we we didn't in our test we didn't think to that extent to see it's heating up across a really big range of the temperature changes.
So I did like your approach of using kind of taking the signal, augmenting it with so many different channels and using that for training. But one question I had is, in wireless communication, you anyway to be able to decode have to kind of estimate and correct for the multipath channel. So why not just do that?
You mean compensate the channel impact?
Yeah. For the purpose of decoding. Why not kind of do it on the raw signal for the purpose of extracting features? And now we don't worry about the channel.
I think people did that.
Okay.
So to use channel estimation to compensate the channel impacts. But from the result they got, first I see the result they got is like compensation will make the discrimination capability of fingerprinting decreasing. Because they compensate, they're not accurately. The channel estimation is you need to estimate. That means it's not real, the channels. Sometimes you compensate more or less, make the fingerprint vanishing during this process. That is the reason exploring why the experiment they did makes the things worse, like the accuracy worse. So based on their results, we think about augmentations because we don't want the signal, the amount of information used for fingerprint just because our bad compositions is disappear. That is the reason.
So the other question I have, so some of these past works also use the channel as a fingerprint. Right? They assume you don't move, and so whatever your channel is, and I'm wondering if you have an opinion on kind of using kind of the channel versus using kind of the hardware. I mean, you've done that with the RSSI in the wearable project, and so what's your kind of view on using the channel as a fingerprint versus using the hardware imperfection?
So there is several things I want to mention here. So channel fingerprints, there's different type of channel fingerprints. They are using either what, in my opinion, like low resolution matrix like RSSI or QI, such kind of informations, to fingerprint the transmitter. And that, instead of using for identify the transmitters, are mainly using for localizations. And that method is a kind of people deploy that, especially deploy that in a scenario where they need multiple measurements at different receiver to collect enough data to describe the transmitter locations. And that needs extra data collections And also it's relied really heavily on the assumption you mentioned. It's relatively don't change.
Mm.
And if you want to use even more precise channel fingerprints, which you use the channel condition to more clear estimation about the channels, that even rely on more strong assumption about the channel doesn't change. Because the fading, there's a lot of things is time variance. In our daily, it's really difficult to achieve that level of things. So that robustness to that method is not that great.
Mm.
That is also the path we went through. At the beginning, we just think about how could we identify the transmitter, and we simply start with RSSI. And we find it's rely on really strong assumptions on the scenarios. And in addition, it actually, with that we use RSSI, it doesn't have really good discrimination capabilities because it's really easy to mitigate.
But one thing in that project I didn't get is how I totally got how you were able to distinguish the on body versus the off body, right? Because obviously when you put a device on your body, like the RSSI changes. But how are you, or why do you think you were able to distinguish on body versus on body attacker versus on body user?
That's based on assumptions, which is in our tech model, we based on assumptions to say the device is deployed on different parts of the brain. So we have the assumption to say it's not really close to your legitimate devices. So the pattern of your movement is different for different part of the body. That is being used to
And do you think like different body types will also kind of have different RSSI, or you think just the location?
That's really matters for it matters for different people, different test people. We observe we only test two. That is the first work I conducted. We only test two people. We already see the difference between because we focus on the walking posture and different people they have different gaits. So that's already different. So a difference. And other people also previously, several years ago, used the gate, this kind of RSSI, and to find the gate pattern to use it to identify different person.
So next question is, you explored different hardware imperfections as kind of fingerprints, right? And evaluated them. And I'm wondering, kind of, did you find that one of them is more stable than the other? Like, which is the most stable, which is the least or robust in terms of identifying kind of, or unique, right? Maybe they're stable, but they're not kind of unique across devices, which is the most for unique and most robust for identification, which is the least. And then another part of the question, which is the easiest to spoof and which is the hardest to spoof for an attacker to come and say? Because, I'll give you an example, something like CFO, right? Carrier frequency offset. Well, the attacker can shift his oscillator a bit to emulate as if he had the same carrier frequency offset as kind of distribution as your device, right? So I would imagine maybe carrier frequency offset is easy, but like non-linearities maybe are hard. So I don't know. But I'm wondering, like, so which is the most robust and which is the easiest to spoof?
So we did the simulation for different. So what we observed, frequency domain features is of course more robust to different channels, especially when you talk about the Doppler effect. This one's really strong. But frequency domain features. In our this work, frequency domain features. First of all, we only have one, and for that scatter we have two. It's only two-dimensional in frequency domain, and it doesn't give us enough information if your number of devices increasing. That is why we have other features also. And in terms of like you say, which is easier to spoofing, I think I agree with you. Like the simple features like frequency offset, like carrier frequency offset, is much easier to because it's like more obvious difference, and also oscillator frequency is easily to tune. That brings into easy to spoof. But other things, like constellation, this kind of fingerprints, the things is like even you adjust it from software. Like you say, I added from a specific symbols, I add a little bit more. It will not go the direction you intended because when it passes through the signal generation process, it will change in a way which adding much complexities. So you don't. It's not
because it's not linear, not entirely linear.
Yes,
like
it's not entirely linear, and also because of that reason, it's more difficult for attacker to control how much they want to change, to which directions. That brings in to the complexity brings in the security level. So
didn't you imagine that like a powerful attacker who would, let's say, extract your let's say fingerprints the same way the receiver is extracting them, and then they would keep modifying their transmitted signal from the digital part, right? And maybe tune the oscillator and keep making these modifications until they match your fingerprint.
yes,
Like, is that possible, or yeah? So what you're saying is no, that maybe that's not possible because it's not clear how that attacker knows, kind of is able to predict exactly how, if they change certain parameters, how it will appear in the fingerprint.
yeah. This question involves different aspects.
Okay.
First, I will say there is research work conducted to play the role of a hacker, try to mimic. As far as I know, they are rely on really precise signal generators and also really high resolution signal acquisition and processing to estimate. And of course, they are using a
So I guess what you're saying, well, if you're gonna, if the attacker is willing to spend $100,000 on kind of very expensive devices that are very precise and accurate, they can do that.
they can do
But
that.
but if kind of then no one kind of, it's very rare to kind of.
Because you mentioned the words you said, like if from software.
Yeah.
If we can, that means if you have, in my understanding, if you're asking if for a like normal transmitter, is that possible?
Yeah, to
just from-
change the digital signal
Yeah,
that
change
you
it.
send to the DAC before, such that when it goes, when you extract the fingerprint, maybe not just as well as kind of maybe the amplification and the tuning of the oscillator, but it's kind of mainly, let's say there are nonlinearities at your amplifier that are different than my amplifier. Can I kind of try to emulate that in the
In
digital, in software, so that when you extract the features, you get, oh, it's the same nonlinearity.
I haven't seen the work which is fully do that. I see a work published actually this year. They are focused on the carrier frequency offsets. They are adjusting from software point of view, like what you said, similar to the message you said, and for BAE. And they are trying to stand at the privacy point of view to say that can be can be used to identify different transmitter, and we don't want to leak out privacy, so we hide this carrier frequency offset. But I didn't see a really accurate mimic work, which is mimic other things also. So yeah, so if it's that can be achieved, that is a question mark, because how much you can control, to which extent, to mimic to how similar you have for the real fingerprint. That is a question mark to be.
So one last question in the so you when you classify the emitters and the tags, you're kind of, when there's multiple emitters, it's like you're classifying pairs. Is that like you have 6 and 10, so you're kind of classifying 60 different categories, or is it that really that you classify each one independently?
Maybe this is a way. This is also the review we got from the PMC.
Yeah.
I think it's the way we write. It's not in a really clear way.
Yeah.
What we do is when we classify tag, we not classify the pairs. So we are just blindly see the tag label is A, B, C, D, and we classify them regardless what emitter they are using. So this is the way we really did, and we also compared it if our training data and also training and test data in the cases which is only 1 emitters, vs like if we have this kind of multi emitter scenarios, we see it of course will be more difficult in multi emitter scenarios. And but it's
the multi-emitter, it's not like all the emitters are transmitting at the same time. Right?
No, we do it
yeah.
like round robin,
Okay.
like to go through each tag and combination with all the transmitters. We do the test.
So you get 60 different combinations.
That's true. We
Okay.
got 60 different combinations between the classifier, but we didn't care about the emitter labels. We just directly classified it.
So, so I'm gonna stop
Okay.
here.
Yeah.
Thank you very much for answering all these questions. So it's a really nice discussion, and we'll just hear it up.
And we start.
Mhm.
So we have the work, and let's say we are in industrial context, and we did have a medical work methods ready, and we want to go
Mhm.
get sense of how we control the emitters. The task to be say a particular back.
Sorry, are you asking the first part of work or the fingerprint? Okay, okay, Yes. Yeah.
So what I'm asking is, are we expecting 5, 10, and
Mhm.
of in this, and are we expecting solutions?
Okay.
In such a time.
So I feel like if we're talking about the backscatter, that's really become a problem. It's almost like it's a problem because you need close range between the tag and transmitter. So you need to tag and emitter. So you need to deploy multiple emitters.
Yeah, I mean, for
Yeah, for Judo, it will be much better in terms of like, it will, I think it will, because if you would consider the same communication distance as we marked the longest one, and for Judo, for other backscatter, maybe it's only need, it requires 1 meter's range between the tag and transmitter, emitters. But in our case, 100 meters. So you can think about it. We are deployed relatively hundreds times less emitters. That will cover. We also brainstormed that scenario actually in a discussion with me and Ambush. It gives that chains maybe in 1 floor or even 1 buildings. You just need 1, and really weak signal already can injection lock the tag. So you don't need that many emitters. Yeah.
covering a big bit.
Yeah.
In the city, how they are being received by multiple absolute
I think that touch another aspect about multi-tag for existing problems. If you want, for example, that is more like if you have several tags, and if you want them to run at the same time, you need somehow, for example, even time division or frequency divisions to handle that concurrent thing.
Okay, so we're talking about.
Yeah.
So you're saying you go one meter and multiple times, the meter might also play to be made out of flow. Say you let's say that this in addition to creating stability, it could also
Maybe the tag handles the TDMA part, or even the emitter doesn't need, I think it doesn't need to really on and off. I don't think it can just always on, but the tag need handle this complexity about concurrent running different tags at the same time. And there is might be a way, for example, if you think about the frequency deviations also can be play a role. For example, different emitters, they are at different frequencies. Yeah.
yeah,
Yes.
I don't think that's how you avoid interference, like interference.
Oh, you can hear at the same time. Yes, that could the frequency of the carrier can play a role to make them to easily to concurrent running different tags.
Like, do they come on the go? Are there time periods when you got spikes? Others when you don't? Or say if you had a tag and you flagged it the window throughout,
Yes, you see, because that depends on the environment, changing environment dynamics. So, actually, the one we did with the free running mode is when it's at night. So the building is empty, it's quiet. So that stability is can support it, have a good communication range. Okay.
or like getting rid of the signal. And we are just on the. So consider locally perceived if it's experiencing like a period of good stability and sort of send, but if it's experiencing high instability, high brain, the performance could be.
I think yes, because by default, if it's, but it depends on the application requirements, to be honest. For example, if you say, okay, I don't need that time, I don't need that data at the particular time, and I have quite flexibility, it can deliver earlier or later, it doesn't matter, that mechanism will work. So it could to say, I just find the channel which good for me, and then I conduct transmission. But I would say more commonly scenarios is you have certain requirements about the time, and you want it to be delivered at a specific time frame. So that it will be more difficult to just leave this instability alone and let it sense when it needs to transmit. Yeah, I think that would be. Okay.
In line with the factory design and reading the papers, we can actually make it work.
Racings.
It doesn't.
Yeah.
I mean,
Yeah.
none.
So I think so. I don't know. I will not think from the manufacturer point of view. I more think about the lesson we learned from this. The first one is a lot of try and testing. So because this work, why it become like the way it looks like now? Because based on this work, it depends on the thermodynamics data from Amber's previous work, but it's different in terms of in last work, he tried to fit the signal into the circuit, but anyhow, we didn't find a way to really, in a good way, to achieve the mixing. How it is that we just do a bunch of the testing from different boards to mixing it and to check. So there is a lot of exploration happening and hands-on exploration happening. So, and during this process, it deeper our understanding about the phenomena, because a lot of things happening for thermodynamics and also the quantum tunneling phenomenon behind the thermodynamics is not that clear, can be explained by equations. So you get a feeling about how it performs, and you go back to history to see the documents, a bunch of documents, different theories, and try to explain like why, and try to justify and criticize about what is really happening. So this is the most interesting things I feel from this work, but it's based on a lot of hands-on trying and also you thinking. So you need to reasoning together and pushing these things forward. So I still remember the day we find out the mixing properties is actually at the beginning, we all stuck in the context about backscattering and thermodynamic things. And then from this behavior, we just have a discussion about it's maybe just like the normal mixing, like signal. The mixture is just a mixture. So how about we just try the mixture way to do that? And then we figured out it could be done like that way. So it's very fun to think and try and then step back and design a system based on the properties and do the things. So I don't know if I answered the three factors. Yeah. Yeah.
I have a question that follows on last one. Would you draw inspiration from much lower frequency use of negative resistance? So how many of guys love to make homemade oscillators without crazy? So it's quite an active set of people making their own negative resistance oscillators by taking up one force rather than whatever. And aside from the frequency, first blush at the level of a high level diagram, what they do is it's building an LC tank circuit with such an oscillator and then literally mixing a voice signal in this case with a circuit with much lower frequency. So is that something that you is it completely incidental, or you draw some inspiration from there? Or?
I would say like I'm not really an expert to design like electronics and also oscillator specifically. The major inspiration we got is actually from the first reflection amplifier work from Francisco Mato, and he made the major innovate. I think inspiration. I don't know where he got it, but he figured out the thermodiode. It's similar way. It's just like generative way to design oscillator, but because the thermodiode property, it can operate at the RF frequency band. That brings a lot of usage can be used for communications. So that is, I would say the inspirations about the thinking path may be happening for him, but we are inspired by his work mainly. And And then from the reflection amplifier continues to this stage, which doing the like this transmitter.
Then it seems that so the injection rate is fascinating. I wonder as well, is it not? There's obviously the instability and the injection lock almost certainly related. So the way that the system will lock onto your dominant HCA transmitter.
Yes, it's
Is probably sort of what's happening with being unstable. For example, you mentioned doing those tests at night. People have RF noise from all of that, and so on. But I wonder, is it sort of would give me hope that, kind of an extension of that circuit just goes to the feedback mode, because if it were if there were a decoupling between input, which is access to be received on the antenna, then presumably you get right to where you want to be. Yes.
I think that is the way we want to go.
Yeah.
For sure. Because as we during the discussion with the panel, I also mentioned these problems. Like that is a game changing point about this transmitter, I think. But we didn't it's need quite a certain of like really like engineering part. So you need to be really find a way in the RF circuit design to make it isolated. And we didn't achieve to that point. I just need to say, we didn't achieve that point to find a low power and the good way to isolate that. So that is why we are, in our current, this design, it's a really obvious problems. Yeah.
And then thinking about the injection, there's something that I didn't fully get. Like, in the case that you're providing that nice big 868 signal here, it's natural that you expect to be able to lock it down. How do you lock things accidentally? Things you don't want to lock to.
If it's at the close frequency.
Yeah, sure. Imagine an industrial scenario, lots of stuff in the factory, using all kinds of different protocols.
Yes, you will. If it reach certain amount strings, you will injection locking any signal surround.
And how selective is it in terms of frequency? So I mean, you have a particular kind of antenna and so on. So, but is it like how broad is the frequency selection you can come up with?
Oh, what we did is like it's easily can lock to kind of like I would say a few to tens of the kilohertz. This range, it's the region which it can be injection locking a good performance. So if you think about if this is really high, no, it's not like for example 1504 that is 250 kilohertz the bandwidth. So it's not that really high. So if it's outside, it's more difficult to injection lock it. You need them to be close. That can give you better injection locking phenomena. Yeah.
Then maybe do you think that the efficiency or performance of this kind of system would luckily change frequencies? It feels like, for example, if you were to just say, "Wow, it's hard to be precise enough," I'll do something where I have a very wide channel band, then you immediately get to kind of big problem.
May I elaborate this question you ask? Is like, is that if you signal is actually at narrow band, your transmitted signal?
Yeah, so move to, for example, I have no idea what I stopped working. Decision of your.
You mean that point?
To be honest, that's an interesting thought. I think it's like if the tunnel diode for sure it can reach gigahertz band. So it's just our work. We focus on the sub-gigahertz for long range this purpose. It can be tuned to the gigahertz band. And for gigahertz, if you have a wideband signal, if that's the instability will be less problems. That's actually a really good thought, to be honest. I think it will give a certain benefit to that. Oh, for sure. So it's actually a really good scenarios to use in a wideband communication cases for tunnel diode when these things doesn't matter any longer too much. Yeah. Yes. But one thing I want to add up here is in case if that signal is clean, it can improve the stability of tunnel diodes. And then it means like, yeah, then it means like if you got improved, you reach the goal why you want injection locking.
Yeah.
So
It's not that.
yeah, so it's not if you have multiple, if you can use other signals to injection locking, that's also one really good point to do the system.
I have a question about the power. First, there were circuits convert. Now, one thing to do, stand out and you can do that. Efficiency conversion. Why is that? Why do you
Efficiency internally in combination with a conversion transmitter.
Yeah.
There's 2 points I want to explain things. The first one is let's regard this the battery part. So the efficiency over the conventional transmitters is actually innovation about the circuit about the industry. The reason behind, as I explained in the presentation, is because this mixture components is operating at really low frequency, really low voltage and current. That region that gives the property it can operate at a low power manner.
I know this is how we will the bias for
A micro.
your operating.
Is that you asking like how to use from high voltage converter to that voltage?
No, I'm in general asking, is the low voltage operation that is that efficiency? Because you basically you're doing
Mm.
you're draining the battery
Mhm.
in terms of efficiency. How many watts power? again, you want to bring. And then the second step is that. So my question is, how much percent efficiency or
We can, I don't know if I can fully answer these questions in my way, but there is two parts you mentioned. The second part, if you radiate a weak signals, like we said, that part is the same for the active radio or for our radio, that part is the same. We didn't gain efficiency from it. The efficiency is the level we drink, like we consume the power from the batteries is a number of numbers. So here we say like the communication radius, active communication radius like the milliwatts level, and we drink it at a microwatts level. So this is in my opinion, I want to answer this question is because the way we design the circuit.
but this could be just CR transmitting.
I think
So I'm
about that, because I did the kind of like related work investigation about the existing SoC, which is including the transmission part. They listed different transmission levels of even for transmission level, the same as what I say, the current oscillator is minus 17 dBm. They also listed some chips also listed. It's still at a milliwatts level. So that part is for sure. It's just so that is what I think that is the things you want to ask about that. I think we definitely gain a certain amount from the circuit design, from the circuit how to drain power this power. And the weak signal